In this module, we will discuss practical approaches for designing biofilm reactors. In the previous modules, we have prepared material balances and looked at analytical or numerical solutions for these models. Understanding and modeling mass transport in biofilms is good, but ultimately we need to find a way to translate our fundamental understanding into practical engineering designs. At the end of this module, you should be able to explain factors influencing the choice of appropriate design surface loadings, and then list ranges for typical design values for carbon oxidation and nitrification. Design surface loadings will be in terms of BOD and ammonia surface loading rates. Finally, you should be able to discuss different design approaches. First, separate design of carbon oxidation and nitrification. Second, considering interactions of carbon oxidation and nitrification for different bulk phase oxygen and loading conditions. A first and very simple approach for designing biofilm reactors is to use tabulated surface loading rates. Here we have surface BOD loading rates to achieve BOD oxidation in different types of reactors. What we can see is that the suggested surface loading rates vary between reactor types. And even for a given reactor type, there can be very large ranges. Ultimately, design surface loading rates depend on desired effluent concentrations, influent wastewater characteristics, temperature, bulk phase oxygen concentration, and reactor operation. Tabulated design surface loadings are often not providing such crucial information and should be used with caution. If we now move from BOD oxidation to combined BOD oxidation and nitrification, we can see that we need to consider both BOD and ammonia surface loading rates. And finally, there are surface loading rates for tertiary nitrification, where BOD oxidation has limited influence on nitrification. A major factor influencing biofilm reactor design is the competition between heterotrophic bacteria and nitrifiers. As shown in this schematic, towards the inlet of the reactor, the biofilm will be dominated by heterotrophic growth. Nitrification will be mostly towards the end of the reactor. There will be a gradient of processes and microorganisms along the length of the reactor. How to design in light of this complex interaction between heterotrophic bacteria and nitrifiers? One approach is to neglect the gradient and to calculate separate volumes for BOD oxidation and for nitrification, as is shown on the right. The volume for BOD oxidation is determined so that complete BOD oxidation can be achieved in the upper volume. The volume for nitrification is determined so that complete nitrification can be achieved in the lower volume. This is a conservative approach, neglecting interactions. The necessary surface areas and reactor volumes for BOD oxidation and nitrification are simply added together. Here, this next design approach is a bit more complex and takes into account interactions of BOD oxidation and nitrification. In addition, it explicitly takes into account the influence of bulk phase oxygen concentrations. This plot on the right provides ammonia fluxes for different bulk phase oxygen concentrations and different BOD surface loadings. Bulk phase oxygen concentrations are shown on the x-axis. The numbers next to the lines refer to different BOD surface loadings. Resulting ammonia fluxes are shown on the y-axis. As expected from previous modules, ammonia fluxes increase with decreasing BOD loading. and with increasing bulk phase oxygen concentrations. Note that this plot on the right is for high bulk phase ammonia concentrations, where ammonia is considered to not be limiting. On the left, I'm now showing a corresponding plot. Different from the plot on the right, the plot on the left is now for low bulk phase ammonia concentrations and for low organic loading rates. The y-axis is the bulk phase ammonia concentration. Resulting ammonia fluxes are shown on the y-axis. Here is now the predicted ammonia flux for a bulk phase oxygen concentration of 6 mg oxygen per liter. Flux of ammonia increases for increasing ammonia concentrations following half-order kinetics up to bulk phase ammonia concentrations of about 1.7 mg nitrogen per liter. With a further increase of bulk phase ammonia concentrations, nitrification is no longer ammonia but oxygen limited. We can now look at corresponding flux curves with 4 mg oxygen per liter or 2 mg oxygen per liter. The initial increase is identical, but nitrification becomes oxygen limited already at lower ammonia concentrations. The rectangles in the plot on the right show the corresponding conditions for 2, 4, or 6 mg oxygen per liter. These design curves consider many of the mechanisms and analytical solutions we have introduced in previous modules. A third design approach provides step-by-step guidance. You find the step-by-step decision support in chapter 17.8.2 in our textbook. I will not review this procedure here in this module, but you are encouraged to review this step-by-step guide in your textbook. Biofilm reactor design is not difficult, but it's also not as simple as using surface loading rates from an overview table. Here's a summary of factors that must be considered. Design and operation must take into account the specific treatment objectives and influent characteristics. Should the reactor be operated for carbon oxidation only, for nitrification only, which we refer to as tertiary nitrification, for combined carbon oxidation and nitrification, for combined biological carbon, nitrogen, and phosphorus removal? To what extent does design and operation need to consider dynamics? How variable are influent flow and load? How relevant are variable effluent concentrations for the given location? Are effluent requirements based on 24-hour averages or based on grab samples? What minimum temperature must be considered for the design? How much flexibility should there be in operating to control aeration and mixing conditions in the reactor? Here are the take-home messages. Tabulated surface loading rates provide initial estimates that are useful for back-of-the-envelope calculations. But these surface loading rates only implicitly consider a range of factors influencing reactor design, for example, temperature, target effluent concentrations. We can use our process understanding to do a stepwise design using our analytical solutions, or to do separate design for carbon oxidation and nitrification. And we can use design curves that take into account interactions between heterotrophic growth and nitrification. Finally, we can do numerical modeling using a simulator to evaluate different design choices to verify or optimize our design. If you have skipped the previous modules on mechanisms and modeling, you are encouraged to review these important concepts. Using simplified design guidelines should be based on a solid understanding of basic mechanisms.